Hi students, to help you on LU7A1 homework, I have explained a couple of problems here. These problems are very similar to your homework problems. So let's focus on the first problem here. The first problem, we are going to study the tensile strength of Portland cement, and there are four different mixing techniques can be used economically. A completely randomized experiment was conducted and the following data were collected. So the data is tabulated in this table here. Mixing techniques, there are four different types of mixing techniques, 1, 2, 3, 4, and each there were four experiments conducted for each technique, right? And the tensile strength was noted for each experiment. So you can see here for mixing technique 1, during the first experiment, the tensile strength recorded was 3129 pound per square inch, right? Now we have to test the hypothesis that mixing techniques affect the strength of the cement, and we can use alpha equals to 0.05, right? So let me show you how to solve this problem using Minitab. So here I have opened the Minitab, and you can see that I have already entered all the values for mixing technique 1. We have four experiments and tensile strength recorded during each experiment. Similarly, 2, 3, 4, and I have all the data here. Now what I will do is I will go to stat, then ANOVA, and then one way unstacked, right? Here we have C1, C2, C3, C4. These are response variables, right? So I am going to select all of them, and confidence level is 95%, which is same as alpha equals to 0.05. So first thing, enter the data in the Minitab, then go to stat, open the one-way analysis of variance unstacked, and then select all the four responses. And then if I want to plot some graphs, I can select for example box plots of data, and now I can say OK. And here I have all the results from Minitab. So let's look at these results. We are interested in this table here. We have factor degree of freedom is 3, which is a minus 1, where a is the number of factors, right? We have 4 factors, so a degree of freedom for factor is a minus 1, 4 minus 1, which is 3. Then we have a total, which is total degree of freedom, which is n, capital N minus a. Capital N is total number of experiments. So we have total number of experiments 4 multiplied by 4, so 16, and 16 n minus 1. 16 minus 1 is 15. So total degree of freedom is 15. Degree of freedom for error n minus a, which is 16 minus 4, which is 12, right? Also Minitab calculated sum of squares values for factor, error and total, and Like here you can see sum of squares, degree of freedoms, and it also calculated mean squares here, and f value, also p value. Now you can see here p value is very small, it's almost 0, right? So p value is less than value of alpha. Our alpha value is 0.05. So p value is less than alpha value. That's why we should reject the null hypothesis. And what is the null hypothesis? Null hypothesis is the mixing technique does not affect the strength of the cement. We are rejecting null hypothesis. That means the conclusion of the study is the mixing technique does affect the strength of the cement. So that's about the first problem. Now also I wanted to explain a little bit more about this problem. I wanted to tell you is if you right click here and go to stat guide, you have some information on one-way ANOVA on stack. If you read this, you will have a better understanding of one-way ANOVA and how to calculate the parameter values using Minitab. Right? So good. That's all about problem 1. Next problem is problem 2. Here we need to calculate some missing values in this table. A computer ANOVA output is shown in this table, and we need to calculate the values for these question marks. This is a table 3.3 from the book. I have copy pasted here. This table is very important, and we will use this table to we'll use the equations given in this table to calculate these values, right? For example, the degree of freedom, total degree of freedom is given by n minus 1, right? N minus 1 n minus 1 is 29. From this table you can see 29, therefore n equals to 30, right? Next is, if you look at the table, degree of freedom for error, n minus a, which is equal to 25, right? So 25, therefore 30 minus a equals to 25, right? And therefore a equals to 5, right? What is a? A is degree of freedom for the factor. A is the total number of factors, and the degrees of freedom for the factor is a minus 1. So a minus 1, 5 minus 1 is 4. Now to calculate the sum up square for the factor, we will again look at the table. We know SS sum up square for the error and sum up square total. We know these values here, right? And we know the expression that sum up square for error is equal to sum of square total minus sum of squares treatments. So we know SS sub t, we know SS sub e, and we know that SS sub treatments is equal to SS sub t minus SS sub e. So SS treatments is equal to SST, which is 1174.24, 1174.24 minus 186.53, right? 1174.24 minus 186.53, which is 987.71. 987.71. So now next we need to calculate mean square value for the error, and we know that mean square value for the error is sum of squares divided by degrees of freedom for the error, right? So sum of square is 186.53 divided by degrees of freedom is 25. We get 7.4612. 7.4612, right? Now we need to calculate f value. F value from this table, you can see here, which is mean squared treatments divided by mean square error, right? So mean square treatment, which is mean square factor, is 246.93 divided by mean square error 7.4612. So I will put these values here, 246.93 divided by 7.4612, and the value we get f value 33.095. 33.095. Now we need to calculate p value. We can find the we may not be able to find exact value of p because we don't have all the tables at the back of the book. So we can at least calculate the bounds on the p value, right? So go to the appendix of your book and you will see f tables there. Appendix 4, which are f tables. I cannot show you those tables here, so I found some tables on internet. Now our degrees of freedom, like if you now in these tables the degree of freedom, first degree of freedom is on in the row here, and second degrees of freedom you can see the values in this column, right? What is our first degree of freedom, which is degree of freedom for the factor, which is 4, and second degree of freedom is degree of freedom for the error is 25. So, and this f table for alpha 0.01, for the value of alpha 0.01, right? Similarly, I have tables for 0.05 and 0.1, right? I can look the value of f in any of these tables, but I will search 0.01, right? So in this particular table, as I said, the degree of freedom is first degree of freedom is 4 and second degree of freedom is 25. So first degree of freedom 4 here, and I will go down. Second degree of freedom is 25 here. That means this value here, 4.177. That is the value of f at alpha of 0.01, first degree of freedom 4 and second degree of freedom 25, right? But the observed value of f is 33.095, which is greater than value of f at alpha value of 0.01. That means p value, our value p should be less than 0.01, right? If I had tables for lesser value of alpha, right now I don't have tables here, But if you have tables of f table for alpha value for 0.001, then you can further look in those tables, and you may be able to say that p value is even lesser than 0.001. Or if you want to calculate the exact p value, you can use Excel spreadsheet here. Or if you want to find the exact value of p, you can use Excel. Here I will insert a formula, dist formula, right? This formula returns the f probability distribution for two data sets. So I'm going to use this formula, f dist. Now x value, which is my f value 33.095, degree of freedom, first degree of freedom was 4, second degree of freedom 25. So exact value of p is 1.18 multiplied by 10 raised to 10 raised to 9, 10 raised to minus 9, sorry, 10 raised to negative 9. So very small value of p. We have calculated all the values in this table. So I think now you will be able to do your homework properly. If you understand these two problems I have explained here, there should be no problem for you to solve the two homework problems. Thanks. Bye.